In this video, we will discuss different units of concentrations and also how to dilute and make standard solutions. So a dilute solution, that is going to be a solution with less solute. So that means that if I have a beaker and let's just say the water line is there, maybe I have something that on a particle level might look like that. And then what I can do is I can look at what it might look like if it's more concentrated. That just means more is dissolved or that it has a higher molarity. Okay, more moles per liter. Okay, so it might look something like that. Okay, there are other concentration units actually, and we talked about mole fraction in the gases unit, and mole fraction is just what percent of your total moles are a certain type of moles. So this would be if I take, let's say I had a gas mixture of like oxygen, nitrogen, and hydrogen, I could say moles of oxygen divided by total moles, and that would give me what's the mole fraction, which is like an italicized X of oxygen, and you can do some things with that. What we commonly see is molarity, and molarity is for sure the most common type of concentration unit, and that is just moles divided by liters. And you should be familiar that every time you deal with molarity, you need to write out the formula, because whether you're in regular chemistry or AP chemistry, you'll always get a point for doing that. And you need to be excellent at molarity because we will see it a lot. There's actually another type of concentration unit that used to be really common a while back, maybe like 50 years ago, and it's much less common today, and that's called molality. And molality has the symbol of a lowercase m, but it's a little bit italicized, and that is moles of solute divided by kilograms of solvent. And that is actually on your formula sheet. If you flip your laminated periodic table over, it should be on there. And this is probably the only unit that we will see this molality, okay? This is only in this unit, and we will use it later on in a later set of notes where we deal with how boiling points and freezing points may change with concentration, and that specifically needs to be molality. But besides that, don't get hung up on molality. It will be a little bit tedious and annoying to use, but after we're done with this unit, we won't see molality again. Okay, so let's talk about how to prepare a solution. We have done this actually. I believe we did it in Unit 8, the unit of the mole, but we're going to talk about it again because it could show up on this unit's test, because this unit is specifically all about solutions. So the first thing you want to do is make sure you do all your math, okay? Have all your math figured out. And the best piece of glassware is going to be a volumetric flask. And if you remember, a volumetric flask looks something like this. It's got one marking on it, and that means that it's only good for measuring this one marking. So if this is a 250 milliliter volumetric flask, it can only measure 250 milliliters, and we know it has done that once the bottom of the meniscus, which I'm going to draw here, is on that line. So you might get something that looks like this. Okay, a common mistake that people make is they think that the top of the meniscus is where they need to be, but in reality it needs to be the bottom of the meniscus, so something that looks like that. Okay, and then what you're going to do is you're going to add your solute, so put whatever you have, typically it's a solid, in here, and then just fill it while swirling till the solution, the bottom of the meniscus, is at that calibration line. Okay, so here is what we're going to do. We're going to do an example problem, and it says, describe using lab equipment and calculations how you would prepare 250 milliliters of a 0.707 molar sodium nitrate solution. Well, the first thing we need to do is do our math, so molarity equals moles over liters, and the reason why it's helpful to write your molarity formula is you can see what you can plug in. So 0.707 equals X moles. We'll have to solve for moles of sodium nitrate, and it's got to be liters, so 250 milliliters. Hopefully by now you can say that that is 0.25 liters. And then we'll cross multiply. We will take 0.25 times 0.707. And this variable x is 0.17675 moles of sodium nitrate. But remember, in lab, I never ask you to go and measure moles. Typically, we measure grams, so we need to get these moles to grams because that's what we'll actually do, or what we would do in lab. And so I'm going to take 0.17675 moles of sodium nitrate, and in 1 mole of NaNO3, there is 85.00 grams of NaNO3. And that gives me 15.0 grams of sodium nitrate. Okay, so now I've done all the math. Now I just am going to explain what to do. And so we're going to, step 1, we're going to measure out. And this is assuming you put on proper safety goggles and gloves maybe. Measure 15.0 grams of solid NaNO3. Step 2 is I would add to a volumetric flask. Specifically, we need a 250 milliliter volumetric flask. And then I'm going to fill to calibration line with not just water. You need to mention that it's distilled water or deionized water. Those two things mean the same thing, but we're going to fill to the calibration line with distilled water and probably swirl while doing so. And so now I should have 250 milliliters of 0.707 molar sodium nitrate. Another common thing that happens in lab is typically some solutions you may buy or you may use and they're just really concentrated. And so diluting a solution is where you add some distilled water, and what it does is it gives you volume, but without adding any extra moles. And so if you think about your molarity formula, molarity equals moles divided by liters, we're adding more liters in the denominator. And so since we're dividing by a larger number, that will decrease your molarity. Okay, and so what might happen is if I were to count all my red particles here, let's say I had 5 molar of a solution, and it looks like we've maybe even doubled the concentration, and so, or excuse me, doubled the volume. So maybe this is 2.5 molar now because we're dividing by double the liters. But if I counted my red solute particles, I probably have the same amount, okay, because I've just diluted it. There is a nice dilution formula, and what it is M1 V1 equals M2 V2, where M1 represents the molarity of what's your initial solution. Sometimes it's called the stock solution. The volume is V1, volume of your initial solution. And then M2 represents the molarity of your ending solution. And then V2, this is one that people commonly mess up. V2 represents the total volume of your ending solution. Okay, so V2 is total volume. I'm going to write it here because people commonly mess that up. Total volume. Okay, so let's do some practice problems. And it says we need to find the volume of a 3.2 molar hydrogen bromide stock solution required to prepare 150 milliliters of 0.4 molar solution. So what this means is I'm diluting. M1 V1 equals M2 V2. And my initial molarity is my stock molarity, which is 3.2 molar. And then my new molarity, it looks like I'm diluting it down to 0.40 molar. And it looks like I need 150 milliliters total of that solution. So I just need to solve for V1. What I'm going to do is I'm going to take 0.4 times 150 divided by 3.2, and what I end up getting is that V1 equals 18.75 mathematically, but you've got to think about the units. Think back to gas laws. If this is milliliters on this side for volume, then when I solve for V1, it will also be milliliters, okay? You can only use milliliters with molarity when there's milliliters on the other side of your equation. That way, they end up canceling, and you don't have to do any extra converting. Okay, in B it says we've got 15 milliliters of a 3 molar solution of nitric acid, which is hydrogen nitrate. And we want to prepare a final solution with a concentration of 0.6 molar. Okay, we want to find the volume of the final solution. So write the formula that you're using always, M1V1 equals M2V2. The initial molarity that we're working with is 3 molar. We want to bring it down to 0.60 molar, and we want to figure out what that total volume is going to be for our solution. And we're going to take 15 milliliters of our concentrated solution, our concentrated stock solution. So V2 equals 75 milliliters. That's what the total volume of your solution will be. Now, problems A and B are pretty straightforward. Problems C and D are the types of dilution problems that you should expect to see on any sort of test or quiz. Okay, what we're going to do is in C, we're taking 400 milliliters of distilled water and we're adding it to 200 milliliters of 0.6 molar magnesium chloride stock solution. And I want to know what the new concentration is going to be. So what is the concentration of your resulting solution? So that's M1V1 equals M2V2. Our stock solution is actually kind of low, 0.60 molar, and we're taking 200 milliliters of it. We want to know what the new molarity is. And then V2, a lot of people are going to say that it's 400 milliliters, but it's not, because remember, V2 is the total volume, and what the problem says is that I have 200 milliliters and I'm adding 400 milliliters, so this is actually 600 milliliters of total volume. So M2 will end up being 0.6 times 200 divided by 600, 0.2 molar. Okay, and so in D it says how much water needs to be added to 500 milliliters of 2.4 molar potassium chloride in order to make the solution 1 molar. So that we are diluting. M1V1 equals M2V2. Our stock solution is 2.4 molar. We are taking 500 milliliters of it, and we're going to dilute it down to 1 molar, and so we're solving for V2. When you do the math, V2 is 1200 milliliters, and a lot of people are going to say that that's their answer. But here's what the question is it says how much water needs to be added. V2 is not how much water was added. V2 is total volume. So what I need to do is say, well, if I had 1200 milliliters to end with, and I had 500 milliliters to start with, that means I added 700 milliliters of distilled water. And that is your final answer.